Okay, guys.
Speaking of devil, when did you get back?
Wayne.
Oh, really?
So, we have a treat for you today. Dr. Salinas and I have known each other for probably close to 4 weeks.
A couple of weeks, yeah.
Yeah, a couple of weeks, yeah.
That math doesn't work.
Anyway, actually, Juan was actually my supervisor when I did my master's degree back in a few years ago. And Juan was the wood professor. He taught wood engineering at Carleton for many, many years. And not only did he teach the engineers, he also taught the architects, which is a feat in itself. So without further ado, I'm going to hand it over to Juan, and he's going to teach us a little bit about wood, about stuff you probably never wanted to know, but you're going to know.
Thank you. I was born in Mexico, so I speak Spanish, but I came to Canada 50 years ago, and decided to stay because I liked it. So you may notice a slight accent in case in my speech. I'm a civil engineer, structural engineer. I've been working in structural engineering for 60, well, I'm 80, I turned 80 last summer, so all my life. And I never took a course on wood, never. When I was in second year of strength of materials, my undergraduate, we learned steel and concrete, pavements, not a word about wood. And so somebody asked, what about wood? Oh, yeah, I think we use 10 kilos per square centimeters. That was my course in wood engineering. So when I came to Ottawa, I did my PhD in Calgary. I did my undergraduate, my master's, my PhD, postdoctoral in concrete. So I'm a concrete guy. So I came to Ottawa. I was teaching at Carleton. They asked, well, what do you want to teach? I said, well, concrete. Oh, well, we already have 4 guys that do that. So, anyway, so I teach whatever you want me to teach. I ended up teaching highways, University of Ottawa. And I still didn't know anything about wood. And one day, in '75, there's a local company, well, Minto, they were testing a wood floor under fire at the National Research Council. It was a multi-million-dollar testing. It was a full floor, all wood, with a loading system, with a fire underneath, and the Research Council, they wanted a professional engineer, I was a professional engineer, to witness the test, to certify that it was followed all the procedures and everything. So I was curious, but about anything about wood. So anyway, so I was there, and everybody was expectations about the fire, and they turned on the fire, and it was going, ready to push the button to put the load on the floor. Back then, the whole thing came down. Somebody made a mistake with the hydraulics, and they put the whole load in 1 second. And usually, tests for fire, we want to test how many hours it lasts before it falls. Well, this one lasted 1 second. So, anyways, and then I realized how little did I know about wood. I mean, the engineers from Minto, they knew, they were young people, they were knowledgeable. And I realized, so I decided to learn wood. So I never took a course, but I taught myself. I read everything I could on wood. I went to meetings and everything. And soon I started supervising students. Before your master's, your undergraduate, he comes and the undergraduates, they have to do a final project. And he wanted to do a wood bridge. But there was nobody in the department who knew anything about wood. So I had to learn to supervise you. Anyways, so I did a lot of work in wood, and I learned a lot, and I did a lot of work. I even made a course for wood engineers. What I want to do today is, any engineers in the group? What kind?
Mechanical.
Mechanical?
Electrical.
Electrical?
Systems.
Systems?
Mechanical.
And mechanical, okay, excellent. So I can speak a few things without problems. I'm gonna go, I believe the way I told myself, let's learn the most basic components of wood. And then after I know this, I can extrapolate to what do I do with a 2x4? So first I'm gonna look at the atomic structure. But don't worry about it. This is not a scientific lecture, okay? It's just to give you an idea of what's going on. After I gain all that knowledge in wood engineering, I have done work in wood engineering in every country in this continent, except for the Dutch Guyana and Paraguay. I have worked in every country, from the north to the south. I have worked in Vienna, in Germany, Finland, in Denmark, in Spain, wood-related work. I gained knowledge at that level where I could converse with people in those countries and do some work, okay? And when I talk to people about wood, my audiences, they haven't been as friendly as this one. In fact, I remember I was asked by the Ministry of External Affairs, they phoned me, Canada sent me to Argentina to give a talk to the Argentinian engineers on how to use wood. And obviously they wanted to use Canadian wood, so I was promoting the country. When I got there, it was a group of about 50 industrial people and engineers, and I had a riot. Because the day before Scotiabank, they froze all their all the US dollar accounts because they were delinquent on their loans. And here is this engineer from Canada. What the hell are you doing here? And I was with the attaché from the embassy. I said, what is going on here? I have no idea about these things, okay? So he explained to me, and I explained to them. And I learned at the time, it was illegal to construct wood structures in Buenos Aires. Illegal. Not only is not in the code, not only there is no code to do wood construction, you cannot. Why? Because wood burns. And so I took that as a hint to, I have to convince people that don't want to use wood, what the benefits are, and on the basic properties, okay? And based on that, I went on with this. Well, we end up under the direction of the United Nations, forming a group of engineers and architects, and we came up with a building code for wood for the whole South American continent, okay, from the Andes to the Patagonia. And the engineers and the architects, they were interested. So we had a common language in that sense, and we went from there. So now I have an audience. Anybody here that doesn't like wood? Well, I love this. It's the first time I do this, you know. So be informed, okay? So I'm going to start with the microscopic structure, and then I'm going to grow to. That's what I do. I work with beams and columns and glulam and all engineering. I have built bridges, houses, all sorts of that level of structures. Okay, I know the codes, I know the practice, I know how to do those things. I've done research too. The problem with research in universities, my concept of research is, so this is what we know about something. My idea of research is I want to increase that knowledge and I want this. But that's not what we do in universities. In universities, when we do masters and PhDs, we want to go deep. We take a topic and we go deep in that topic. Okay, and you notice when you go deep, you go narrow. And basically, once you know everything about nothing, you get a PhD. And I get one of those, by the way. So let me tell you. Yeah, I cannot get lower than that. Wood is made out of carbon, made out of cellulose, which is carbon. And the internal structure is a four-sided figure that is very stable. You make one of those out of wood, you cannot roll it. But you make a die, you make dies with 6 figures, with 6 faces, and you can roll those, okay? So this is a very stable atom, okay? The crystalline structure, well, what's the strongest material that you know? Strongest material that you know? Diamonds. Diamonds are carbon, okay? And so we start in very good footing with wood. It's very strong. It's very, very strong. The electrons going around, they're interesting because that's where atoms attach to each other to make molecules. And the molecules attach to each other to make chains, and eventually you get a tree made out of carbon atoms, okay? The internal structure of the molecules of wood is the cellulose, okay? 6 carbons. You start with 6 carbons on the left. That's the structure of benzene. Benzene is a fuel. And for many years, chemists, they couldn't conceptualize how to put 6 carbon nuclei joined together like that. And the story goes that on his way to work, he was riding a bus in Copenhagen. He was Danish, in Copenhagen. He fell asleep and had a dream. And he dreamed of that. And from that we grew with all the, whatever we know. Well, glucose, cellulose, lactose, you know what those are? They're sugars, eh? And that is perhaps the most important reason why I love wood so much, because, well, wood is cellulose, okay? Oats is a sugar. Now, when you submit oats, sugar, to an organic process called fermentation, you get the molecule of the glucose or the cellulose divided in 2. One of them becomes a gas, which gives you the bubbles, and the other one becomes alcohol, which gives you the headaches. Beer, wine, you distill it, you get whiskey and cognac, and I love those things. So that is one of the reasons I keep going with wood, okay? It brings me good memories about that. So the difference between the benzene and the glucose is that the benzene is a flat plane, but the cellulose and the glucose, the tips of the hexagon, they come off the plane. So it's a three-dimensional molecule. So it offers more opportunities for bonding and making chains, this polymeric chains, and these kind of joints are better than these kind of joints. And the strength of cellulose, for us engineers, the strongest material we use in construction is steel. Cellulose is 20 times stronger than steel.
By weight? By weight?
Yeah, very good question. It takes 20 tons to pull one electron out of an atom. I read that. I don't know. I never tested one of those. Okay, but if you could make a rebar made out of pure cellulose, it would be 20 times stronger than a rebar made out of steel. Yeah. Yeah. Good news, right? Well, wait for the punchline. So the polymeric chain, this yeah, right there at those overlaps, they make the hydrogen and the oxygen in the cellulose. They make bridges. They call hydrogen bridges. And then you have an atom of hydrogen and an atom of oxygen and another atom of hydrogen share between these two parts of the molecule. And it's a very strong bond, but not as strong as the cellulose itself. So it's a chain with a weak link right there. Okay. So from polymeric chains, they aggregate 5 or 10 or 15 of those, and they make a fiber, a little fiber, microfibers they call them, small fibers. And these small fibers, when the tree is growing, they deposit themselves into I'm gonna be using this. A wood cell looks like this. It's a cylinder, hollow cylinder. Okay, and the walls is 4 walls. The primary wall, these microfibers are totally random. Okay. The secondary wall consists of 3 layers, and they are organized. In one layer, the fibers go like this. In the other layer, the fibers go like that. In the other layer, the fibers go that. And it's a very strong, very stable, cylindrical container of something inside it. And the tanks for the solid fuel of the rockets that we still use, they took that idea from this. They're carbon fibers, okay, man-made carbon fibers, to contain the tremendous pressures in those cylinders that have the fuel for the rockets. Okay, so you can see a very strong atom, a very strong chain, but less strong, some weaknesses, and then aggregation into fibrils, and then the fibers themselves into a cylinder. Very, very strong. So I want you to take one of these. You want to pass them around?
Sure.
Just one per person, okay? I tell you what, I'm going to give you more later, but I want you to test one at a time. Okay? So, never mind the electrons and the neutrons and all that stuff. Okay, so you have a wood cell in your hands. It's about the right sorry.
No, that's fine.
It's about the right ratio of length to diameter. Did you get? We need more.
I'll come around.
Now, I want you to test. You want to sit down here?
I prefer to stand, but thank you.
That's fine. I always like to sit in the back in a lecture. Because when I was a student, we used to smoke in class. That's right. Well, we're not allowed to, so I used to smoke, and I never thought the professor noticed. Because I was near the wall, near the window, and I kept my cigarette outside. And I don't know how it happened. Somebody came to visit the lecture once, and this was the 60s, okay? And the guy was starting to light a cigarette, and the professor says, no, sir, we don't smoke in the classroom. And then he chose, except for Mr. Salinas back there. He knew all the time. Anyway, so 20 times stronger than steel. Okay? So how are you going to use this wood? Try and pull it. Super strong. You need to grab it. You cannot pull it easily, okay? Now look at this. Use it in compression. It buckles. It doesn't work. That's parallel to the fiber. What about perpendicular to the fiber? What do you think? Weak or strong? No. You have carbon versus carbon. The strain is there, but it squeezes. The deformation is not acceptable. So when we make a wood beam, I'm not worried about if it is the fibers. I don't worry about the compression. I worry about how much it's going to deform. So deformation and strength, two separate things. We need to think about both of those. Okay? And then what about shear? What about sliding fiber against fiber? Well, in the longitudinal sense, how are these cells attached to the other cells? Well, there is a glue, it's an amorph compound called lignin. Oh, lignin it's like caviar for the bugs. That's what we worry about, biological attacking wood. Okay? And there are 6 possibilities for shear stresses in wood. Longitudinal and transversal. They're very strong in shear. Okay? The fibers, in fact, we call this rolling shear in wood engineering. Okay? So from the atomic level, we go to the cellular level and the tracheital level. 2 big distinctions, hardwoods and softwoods. What is the softest wood that you can think of?
Also.
It's a hardwood.
Poplar?
Sorry?
Poplar? No.
Yeah, poplar is
carving,
also soft. It's also
basswood.
soft. But yeah, basswood. Yeah. Okay. So the name hardwood and softwood don't apply all the time, but that's what. So in this field we call them trees that lose their leaves and trees that don't lose their leaves. Okay, caducifolias and conifers. I would tell you, I turned 80 last July. And you get 80, men lose 2 very important qualities at that age. You know? The first one is memory. Yeah. I can't remember the other. So the aggregation of tracheids is different in the softwoods or the hardwoods, and they behave differently. What kind of woods do you use in your work?
Mostly hardwoods.
Mostly hardwoods.
Yeah, some softwoods like pine.
Pine, yeah. It's the opposite in structural engineering. We use softwoods, pine, spruce. Sorry?
For,
yeah, SPF, spruce pine fir. I forget stuff.
Is that a strength to weight ratio thing?
Yeah.
Or a cost thing?
It's always
Both.
cost. It's always cost.
It's always cost.
Yeah, but the way the wood construction evolved with time is a self-depurating system, a self-optimizing system. All the stuff that we did wrong killed the people that designed them, okay? You design a bridge with the wrong wood, you go over it, you fall down, you don't do it again, right? So, one time I supervised a master student, because look at the wood construction. We use studs and plywood. And we use 2x10s and wafer board. It's always a combination of a surface and a rim. That's the way we build airplanes
And boats.
and boats. So I had a friend, a former colleague of mine, that instead of going into buildings, he went into actually submarines, but he was designing airplanes for Boeing. And he sent me a copy of the computer program that you had one of the copies, anyways. So to do the structural analysis of a system that consists of ribs and surfaces. Hey. So I tried all sorts of plywood and wafer board with all sorts of 2x4s and 2x10s. And what is the optimum combination regarding cost? So, you know what we got at the end? It was a master's thesis. The best combination, you want to make a floor? 2x10s with 3/4 plywood. Really? But that's what we do anyways. Well, that's it. Okay? Or, well, what about if you put a load, use this, about a stud wall? Oh yeah, the optimum combination, 2x4s and 1/2 inch. Wait a second, that's what we do anyways. Well, it evolved into that. And the optimization curve is very shallow. It's very shallow. In other words, the minimum cost doesn't change much if you go 2x4 to 2x6. Well, we're using 2x6 studs, not because we need them for strength, but they're still cheap, but we can put more insulation there. And sometimes we find interesting things by doing the deep and narrow, you know. Sometimes advantage of that. So like I said, some of these things you can take advantage of. Some of these things, well, that is going to ruin the shear capacity. That's a beam. You got to be careful it's not in a high shear area in structural engineering. Okay. I don't think you want to make furniture with that. Okay. But we can make toys with those things. And Bill and I are thinking of making children's toys with it. Anyways, I don't know if you've ever seen this. It's like a washboard. You get waves on the surface. Have you ever seen that? No, that happens during the drying process. The wood that you guys probably use is dry under controlled conditions. This is dry on a kiln, on a special oven with a very regulated range of temperature and moisture content and air circulation. And this is when we overdo it, you know, the company wants to do it fast because you want to sell it as soon as you can, okay? And then what happens is that it shrinks so fast that the top fibers buckle and you get like a, what do you call it? This is for washing. Washboard, a washboard, yes. Yeah. Carpeting, sometimes they call it carpeting. It's when you slide on a carpet and it goes like that. Yeah. So, very important concept is the biological attack, and the three ones that I have dealt with. Blue stain, spruce pine fir is very subject to that. Very easy to treat it. Well, at the end of the process of saw milling and everything, and when it comes out to be stored, we put it through a bath of some very carcinogenic chemical. But then that takes care of the blue stain. Blue stain doesn't affect the strength, even if you so it's fine. The strength is fine. Okay. Brown rot. Well, if you find brown rot, if you see it, that's gone. Okay. Once you see it, there's nothing you can do about it. Okay. And you can recognize it because the cracks are perpendicular to the fiber. Okay? White rot is mild. If you let it go too far, it will affect the strength. Okay? There was a case of a timber company in Montana about 30 years ago. A whole thousands of hectares infested with white rot. And it was a red, probably a red cedar. From the west, probably. Yeah. But the stain took shapes. So the engineer says, forget it, we are screwed. Burn it, throw it away. The marketing guy says, wait a second. They made a killing. They made veneer. Beautiful, white and strong pink. Yeah, so marketing. Yeah. Yeah. There's nothing new for you here, okay? But I put all these things in this. I only have 10 copies. I can make more later on, but you should keep those if you want to, okay? Pass them around. I want to talk about connections, because you worry about those things. We worry about those things in structural engineering. If I take spruce pine fir number 2 stud, 2x4, how much your car weigh? Eh?
My pickup truck or the car?
How about the pickup truck?
Probably 4,000,
4,000? No, how about the car?
2,000.
Okay. I can pick up a 2,500-pound car with a 2x4. This is strong enough. No, like that.
On the tube.
Yeah, parallel to grain. Very strong. How am I going to attach a car to a 2x4? Which brings the problem of connections. The best way to join two pieces of wood together is with glue. Forget about bolts, nails, metal plates. Nothing works like glue. But to glue, imagine gluing studs to walls or the floor joists. We never build anything that way. It takes time, it takes control conditions. Has to be clean. Have to put pressure. So we use nails. So take a 2.5-inch nail. Wow. Let's make it a little bigger nail. We're gonna join two 2x4s. How much? What's the resistance of one nail?
Shear?
You have a piece of wood. You got a piece of wood here and a piece of wood here. I have one nail there, and I'm gonna hang a weight. How much can I hang there?
500 pounds.
Not much. Not with one nail.
It's about 160 pounds. Because it's 800 newtons. And I weigh 800 newtons, so 160 pounds, yeah. It's not very strong. No.
But is the correct answer enough? Like if
No, that's failure.
If we hang a weight from something, isn't what we're concerned about is not the actual theoretical value, but is it enough?
No, that's
if we
what-
want to hold something up, then we want to hold.
That's
that
what the
thing
code
up.
says. The code says that.
Yeah.
The code says
Yeah.
if you do it by code, then nobody can touch it. Now, 2,500 pounds. So how many nails do I need to lift up a car? Hundreds of nails. What do you need to accommodate 20 nails? What if you put two nails next to each other? They behave like one.
Your example, the one nail and the 2x4?
Yeah.
What's the failure mechanism?
There's about 4 or 5 different ways it can go, depending on the thickness.
There's a bunch of different ways it can
Yeah.
fail.
But you can have the nail just pulling down and up the other one. That means on this side is failing in compression, in this case parallel to grain, okay?
Okay.
Or if it's solid enough, the nail can go like this, like a Z. That's the strongest one, okay? There are about 4 or 5 different failure mechanisms, and they are all incorporated into the. I was chair of Mechanical Fastenings Committee of the National Building Code. So I had to study. We didn't have any tests, so I had to do. You helped me with some of those things, remember? Yeah. We didn't have any tests. We didn't have any experience with this thing. We have tests that were done in the States in 1939, just before the war.
Is that why plates are used often now in
Those metal
construction?
plates,
Because they have so many nails, effectively?
and we tested every possibility of those plates. We tested thousands of those for Minto, for 10 different companies in the States. And we found a lot of stuff that nobody knew. For example, Minto will call us and say, okay, we have 50 specimens, we need the test, we're doing the results by tomorrow. Wait a second. Wood is very dependent on time. Time factors, you have to take that into consideration when you load a structure, okay? I give the students okay? You have a 2x4, you can break it 2 ways. You have a karate guy goes bang, and he breaks it in one shot. You can have an 80-year-old professor, you can push it like that. And in 200 years, you'll break. Because it accumulates with time. The damage accumulates with time, okay? So time is important. What else did I want to talk about? Oh, I think 5 more minutes?
No, you're good, you're good.
These are some of the species that I don't know. I have 1, 2, 3, 4, 5. I have 10 species that I dug out. Do you recognize those? Do you use those? Yeah. And it tells you what common usages are for those. And these are the other 5. Cedar, pine, Douglas fir, hickory, and ash. Okay. Those are in the, they should be in the handout.
But I think the interesting thing as a furniture maker,
Yeah,
right, is that probably the least important thing on my list of characteristics when I'm choosing wood for a project, let's say I'm building a table or a box, the last thing on my list would be strength.
yeah. Oh, I agree with you.
Because any wood I'm likely to choose is going to be more than strong enough
10 times
for the
stronger than you
task.
need. 10
So-
times
so
stronger.
So I go to the other factors, right?
Yeah.
Workability, cost, color, grain, availability.
Yeah.
Strength is irrelevant.
MAA concept in structural engineering. MAA is a principle we use in structural engineering. It's called the masses are asses. Yeah, I don't have to design a table to resist 50 people,
That's right.
but you know what? Somebody's gonna do it.
But that's lawyers talking, not.
Exactly, exactly.
Sorry, that's.
I used to
that's
give
the
an
bullshit
assignment to
factor.
my architecture students
Yeah,
to design a swing
oh, yeah,
structure,
yeah.
For the
Law
campus.
firm knows.
and they put it right in front of the student center. The student center at Carleton University is the outlet with the biggest beer sales in the province. Beer sales. So what do you think a bunch of engineering students coming on a half-price Wednesday night? And you design, I checked the calculations, you design this swing for 100 pounds. I said, well, you for just the little kids in kindergarten, they weigh 30 pounds. Yeah. M-double-A. Okay, you're gonna get 5 guys climbing on that thing, and they're gonna, now the lawyers come in, right? Because they're gonna sue the university for it, yeah. Anyways. Yeah, that's a pretty good observation there. Connections, yeah, I already talked about connections. The best way is glue, and you guys use glue. And what kind? Well, there are organic glues, there are all sorts of glues. I learned a little bit about glues because we had a case, I don't know if you remember, the companies that were making trailers were using urea formaldehyde glues, and they are carcinogenic. And people started complaining and whatever, they had to change all those. Yeah. Usually prefabricated houses and things like that, you come to a place like this, they tell you what glue to use, right? They know the compositions, okay?
Back on connections though, what about the role of joinery?
Yeah.
Because that gives you the combination, because there's stuff, I mean, the museums are full of furniture that was built before glues
Yeah.
were viable.
Yeah,
And the stuff is holding together because of joinery.
yeah.
So no mechanical fasteners at all,
No,
and no glue.
no. I don't know about the glue, but well, you've seen the Japanese model where they, I couldn't even describe them. I'm supervising a PhD at Carleton in architecture, and the guy he wants to build 6-story buildings by wood with thick walls, laminated. You get a 2x6s glued together like this to make something the size of a plywood sheet. Okay, 4x8. I said, well, how are you going to join it? You know, it's going to fall. He said, well, no. He uses the computer CNC. It's a 3-dimensional joint. It's like this, but there is another, it goes around. I don't know how the hell we're going to put that together, but he knows how to cut them out. Yeah.
So you hire a guy like that.
Yeah. Is that what you do?
I've been involved with some mass timber projects.
Yes, yeah.
Yeah.
Whereabouts?
Where I live in Wakefield, we did a project that had panels from Europe that were 8x40,
Yeah.
2.5 inches thick.
Yeah.
So we wrapped a building in 2 days.
Yeah,
Commercial building.
yeah. But that's
Insulated already and everything.
what we were planning to do with this. Ottawa was planning on building a Christmas market for downtown. And they wanted something that could be disassembled after a month and then put it back together next winter. And so I was working on that. But, yeah. One last thing I want to ask you about. Has any of you use sinkers? You know what those are? These are trees that have been underwater for 100 years. What do you call those?
Petrified
No, it's not petrified.
It's full of water.
or waterlogged?
It's full of water. Call them sinkers.
I know I've hit them.
Eh?
I've hit them.
There's a company around here somewhere, there used to be called Logs In,
Yeah.
that used to recover logs from the river.
Yeah. And
And
did
they
you,
dried it and made flooring out of it, and I had some samples from them 20 years ago.
Yeah.
And the strength is fine, as long as it's not rotted. What happens in the water is that the color may change, because of the local effect of mineralization.
a good friend of mine, I went to school in Calgary, so I made a lot of friends there. And this friend of mine, he was the first violin for the Calgary Philharmonic, German guy. He got an ear infection, he lost his hearing. So he couldn't play the game. So he became a luthier. He makes violins. He goes to Germany. A 10-foot tall, about 18-inch diameter sinker. He pays $20,000 for it.
I know, there's one in the Ottawa River.
Yeah.
I hit it.
Keep it, sell it. They're expensive, yeah.
Wood that's been sunk for a very long time. When they recovered the Mary Rose bow in England, they had over 200 longbows in there.
Yeah.
They spent a great deal of time drying them out, desalinating them, and they managed to pull some of them to 140 pounds draw weight.
Yeah.
Snap.
Wow.
So, that's
Yeah.
very good.
Yeah.
And the weights that they estimated would be up to 120 to 160 pounds. And managed to get some of these up, like, they've been in since, what, 1545, so.
Yeah, yeah.
Yeah.
So my friend, last time I was in Calgary about 3 or 4 years ago, he's always working on violins, because that's his instrument. But he was working on a cello for a German Berlin Philharmonic player. He was already working on it for 2 years. He was going to sell it for $75,000. And he was using nothing but sinker wood. And I read things, there was a temple in Japan or in China, where they recovered furniture that was in a swamp for 400 years. They took it out, they cleaned it up, and there. Yeah.
They're pulling oak out of bogs in England.
Oak?
Oak, they call it bog oak. And it's been sunk in bogs,
Yeah.
And-
Oh, yeah,
and
yeah.
it's fine.
Well, the thing is, they do it from the ocean too. I don't know how the logs got in the sea.
Yeah, I saw I was about to say, I saw the Discovery Channel on that,
I
and
just
you'll
saw
never
it
see
a couple
those
of days
grains
ago.
again either, that's why they're expensive.
A couple of days ago, I saw it
Yeah.
on the Smithsonian.
That's
Yeah.
Have you heard of the
Because
tree?
you'll never see those grains patterns again either, because
Yeah.
it was way different way back
Wait, yeah.
1,000 years, let's say.
If you're a luthier, you know about the tree.
Well,
This is a tree that they dug up in I think it was Brazil, in probably the 60s, and they're still selling matched sets from that tree
Wow.
for guitar making and
Yeah.
instrument making, and a matched set of thin, like bookmark with the sides is worth thousands, like 10 grand or something like that, for one match set.
yeah.
I know a buddy of mine actually had to bend it.
Took them 30 years, it took them 30 years to get that tree out of the jungle.
Yeah.
Because
Yeah.
when they cut it,
Yeah,
it fell down into a ravine.
yeah,
Oh, yeah, I heard about that.
yeah.
You see that happen?
Yeah, yeah.
You know,
So look it up.
I'm gonna look it up.
Look it up,
yeah.
it's called The Tree from guitar making, and it's,
Yeah.
I've
You
seen
know
guitars
the-
made out of it, it's incredible.
You know the bird's eye maple?
Yep,
You use that?
yeah.
Yes, oh, yeah.
You use that. Well, I was doing a job in Ecuador, and I went down to the coast to Guayaquil. Turned out, you never know who you're going to find. The guy in charge of the plywood mill had been my classmate in university. Anyway, met again in Ecuador in the middle of nowhere. Anyways, so he took me to the forest and he took me to a guy that was making guitars. Bird's eye maple, I don't know if it was maple. It was acer, it was that species. But you know the bird's eye maple, the tones of brown and cream, these were blues and pinks and greens. I said, I'd like to have a guitar for you. Well, not as well as he does, but I play the guitar. Don plays the guitar. How much would you charge me for the guitar? He says, well, I don't know, 12, 15,000 bucks. I think that would be a waste of money for me. Yeah. Anyways, so I just wanted to bring that up because there are specialty woods, and I don't know, I see some plants there, I don't know. I don't really know what it is, but if you have any comments or questions, yeah, that's it.
What is spalting? What is spalting? We see it in maple most commonly, but
Spotting, is that a biological attack, you think?
I think it's a
rot. It's a fungus.
I think it's rotting, but I wonder-
It's a
I was
fungus.
thinking back to your white rot versus brown rot.
Yeah,
And spalting can change the characteristics of the wood.
yeah.
And if you catch it soon enough, you don't lose too much structural integrity. I mean, I wouldn't trust it to stand for making stairs out of it or something.
Yeah.
But I'm wondering
What color
about,
is it?
what I'm wondering about more particularly, because I've used it a lot, is when you get a biological attack on, say, spalted maple or ambrosia maple or some other woods, you get a color change.
Yeah.
And the simplest explanation that I have, is what was given to me, is that when the bugs attack the wood, there's a chemical reaction, the wood basically is attacking back, and the color is the kind of blood on the ground. It's the byproduct of that, of one force trying to resist the other force.
I thought spalting was actually a mold.
A mold or a
Yeah.
rot? Now,
It's a
I don't know
mold.
the
Well,
difference.
it depends. The mold, it has a finite time period. It will do whatever it's going to do and it ends.
Okay,
The fungi,
and it dies.
once you see the mushroom there, forget about it. That's gone. Jake, remember Jake?
Yeah, Jake Evans.
Friend of ours, took me to his house in the basement. They forgot to do the weeping holes in the veneer wall in his house. So there was water accumulation. There were mushrooms on the seal plate, on the
Yeah.
half wall in the basement.
Yeah, probably that's fine.
I said, what should I do? I said, sell. Sell as soon as you can. Once you see the fruit, you're done. Yeah, but if it's a stain, that's why I concentrated on those because of that. Now there are biological attacks from the point of view of there are marine borers and things like that.
Yeah.
Anything will build in the water that's there. Okay, but there is a problem. There's no problems here that I know of with termites. Okay, have you ever found any termites?
No, not me,
Okay.
it's just a boulder.
I used to have a bunch of very old maple, and I thought the spalting was a problem, and I ended up getting rid of a lot of it. But I stickered it, and it was out back. It was probably like 6 years out in the weather, and as you took it apart, you'd see little piles of sawdust. So something's actually been boring into it.
Yeah.
Okay, now it could be ants.
Yeah.
It could be.
We did have ants in the house, which is why my wife said get rid of that wood.
Yeah.
And since then the problem
And
has
the
gone
other
away.
ones.
The powder post
Carpenter
beetles.
Yeah.
No, termites.
Oh, yeah, with the bug hole.
I had to deal with termites in
Yeah,
southwestern Mexico. They're all over the place. There are two types of termites: ground termites and wood termites. The ground termites is easy to find because they live in the ground and they eat your house. And in the process to go to the grocery store, which is your house, they make tunnels made out of mud. So if you see mud pipes going into your house, those are hard to get rid of. They have to poison the floor to get rid of those termites, okay? And the difference between termites and ants, carpenter ants. They call it the frass of the termites. You know what the frass is? Okay, with the shit. You know? It's crystalline. It's the form of a hexagon. And I don't want to tell you what it tastes like, but it has a specific taste. Okay, I have tasted it because of furniture. They go for the furniture, the termites. Yeah.
Really?
Yeah. Yeah.
They gotta get in your house first.
No, I told you, this was in southwestern Mexico. Very humid.
Oh, okay.
Very humid, yeah. And there are ways to get rid of them, but yeah. The thing is, wood is a living organism attacked by living organisms. So it's food. Wood is food for the living organism. The only way to protect it is get rid of the food. You cannot get rid of the wood, put it in the yard, okay? But if you have something in the house, you have to take care of it. Well, there are things you can do about it. The best thing is to prevent it, okay? So what we do in structures, we do wood treatment. It used to be green, now it's brown, the treated lumber, okay? But even that is not 100% effective, because in order to, you have to paint. Paint is one way. You see in the sawmills, the ends of the lumber painted yellows and blues and reds. And two purposes, because that's the way the bugs enter, okay? And the color, because we sell a lot of specially sized lumber to Japan. Japan, they still use the 400-year-old dimensions and ratios and things, okay, of the lumber. So we said, you go on the west coast, all the sawmills in northern United States and BC, you see the sawmills with all the colorful number ends in the yards. Yeah. Anyways, I think that's longer than I wanted to.
It's all great.
It's
Are
been
there any
great.
other questions?
Yeah.
That's fascinating.
Yeah. I'd like to thank Professor Salinas, Juan. That was really good, actually. But I do have a little something for you.
Oh, come on.
So as you guys know, I'm a turner.
Oh.
And I'm Canadian. Yeah, that's fine.
Thank you.
Thank you.
Thank you very much. Nice meeting you all. We stay in touch.
Yeah. So we'll take a couple of minutes. And are there any
Just
presentations?
one question I do have.
Oh, okay.
How can you tell, like, this a while back, I had, say, 1x3s or even 2x2s from Home Depot. How can you tell if it's dried properly? Because you get it home within, say, 3 days, all of a sudden it starts, like you said, to,
Yeah.
It's because it was stored outside
Yeah.
in the rain.
you know what I mean?
You
So
gotta-
is there a way to tell before, you know what I mean?
Well, you can get a wood moisture content device. It's a little thing, you put it into the wood and it tells what the percentage is. If it's more than about 12%, wait a minute, okay? And when you store it, make sure it's in a flat place that can
Level out.
circulation, okay? Yeah. If you want to dry it yourself, you have a pile. What I've done sometimes in a construction site, I get a pile and I need to use it like next Monday. So I put the pile with the separate lumber, pieces of lumber, and then I cover it, and I make a fire at that end, and I put a fan at this end. So it draws the hot, dry air. And that works. You gotta be careful. Don't go home and leave it there. You gotta leave somebody there watching. Oh, was it? Yeah. But drying wood is an art. Companies will sell you whatever you want, but they won't sell you the recipe for drying. The drying kilns is a combination of moisture, temperature, and duration. Otherwise, you get some of those defects. Sorry,
We had a lady come in, they actually have a mill out in the east end of Ottawa, and they have a kiln out there, and they dry all kinds of different types of woods, and you can mostly hardwoods and stuff, it's not for
they
construction.
do it for you? They do it?
Yeah,
Oh,
Yeah.
wow, there you go. I'd rather use that.
what's the name of the place?
Clarence Creek?
Wood Select, I think it's called, yeah.
Oh, Clarence Creek.
In Clarence Creek, yeah, yeah. Yeah, she came in and did, one of the owners came in and did a presentation for us over the season. It was really good.
Well, if you just have a couple of pieces you want dry, I'm sure they charge you by the board foot
Oh,
or
probably,
something.
yeah. You just put it in on whenever they're doing it.
Could you dry wood under either weight or some sort of like structure so that it won't deform when you dry it? Like so that it can't twist? Like if you prevent it from twisting and then dry it,
You're just delaying it.
it will happen anyway.
Yeah, it depends on the orientation of the fibers. I tell you one of my quirky things that I did. I learned from a colleague in Syracuse University. He showed me a 2x4, time to a knot.
Oh, wow.
So I said, oh, I had my merchant mind. So I was planning to, the process is involved and it's dangerous. You need a kiln. When the doctors used to sterilize,
Autoclave.
you need an autoclave, I forget what. An autoclave, the pressure and temperature filled with ammonia. Yeah, that's why they wouldn't let me do it at the university. Yeah, and then what I was gonna do, I was gonna put plates like that, plaques, and I was designing like a die to make the finishes on the kitchen cabinets. All sorts of finishes. And it was great because the production rate could be fantastic, okay? And I could sell them, well, practically the cost of the plain lumber plus a little bit of, okay? The problem is that wood is viscoelastic. You get a very nice imprint, like, oh yeah. A couple days later, it's flat again. There went my, that was my, there went my pension, you know? Sorry.
All right.
Thank you.